So now that we have an assembler and we have some debugging tools for assembly language, we'll be able to write some assembler more easily. But we don't really want to do that much. We're going to have to write some as we go forward, some runtime library support code. But mostly what we'd like to be able to do with the assembler is turn VM opcodes into assembly language and then run it that way. So in the end, we should be able to write brew and have it get compiled into VM opcodes. And then this jitter that we're going to build now will be able to take the VM opcodes and turn those into assembly language. And then we can execute the assembly language. So we'll really be able to run our code either with the VM or with our CPU emulator. If we want that to work, there are a few things we need to add to our system. We need to be able to handle syscalls. For now, we're only going to need one. There's a link here that goes to the list of real syscalls for Linux. There are lots of them. Right now, we're only going to support exit so that our program can terminate. The way we make a syscall is we place the number of the syscall in EAX, and then other parameters are placed in other registers, and then we execute the interrupt instruction. So we say int 80 or x80, and that will cause the operating system to catch that interrupt, and then it handles the syscall. So it will kill the program or go read from a file or open a network socket or do whatever that syscall is supposed to do. And then it puts the results in our registers and jumps back into our program at the next instruction. So right after that int 80 instruction, the results will be in the registers. Of course, in the case of exit, the program does not resume, it just gets killed. Operating systems like Linux look for a label in our executable so that they know where execution should begin. By convention, this is called _start. That entry point typically sets up the runtime environment. So if you're running a program that you wrote in C, say, there's a bunch of stuff in the standard libraries that needs to be initialized. It needs to set up the memory allocator and some other things, file handles for the console and things like that. And after it does that, then it jumps into the program's main method. So what the user thinks of as the beginning of the program. We're going to do the same thing, but it'll be a lot simpler for us. We're just going to prepend this small amount of code to any assembly programs that we generate. This will be our start function. So we're going to call main. So we're assuming that the user will have a function called main. And then once main returns, we're going to use the exit syscall to kill the program. So we're going to put 1 in EAX, which is the code for exit. We're going to put 0 in EBX. This is actually where we put the exit code of our program. So if we wanted to return an error to the command line, we could put a different value here, but 0 means success. And then we're going to do int 80, and that will tell the OS, hey, handle this syscall, and it will see that it's the exit syscall, and it will kill our program and return that success result of 0 back to anyone who had called us. So if we were running in a script or something like that, it would know that the command succeeded. There have been a few small changes to the starter files. Our method class did not know what its return type was before. We did know it when we parsed the code, but we just didn't pass it into the method object. So now compile visitor is doing that. Some get methods have been added to a bunch of the opcode classes because when we're turning those into assembly code, we need to be able to get at the details of what that opcode is doing. Our VM language now includes a return type in the function definition. So now it would say function int pow xy. VM parser and the old tests have been updated to handle this. And then there are a couple of new methods in test-util. There's one called VM to asm that will go look at the methods that have been compiled and use the jitter to convert them all into assembly language. And then there's a run asm method that will take a program and it will put the startup code on the beginning of it, and then it will execute that assembly language, and it returns an array of the local variables from the main function. So this is really handy for testing. So to implement this, there are a couple of things we need to do. We need to add the int instruction to our assembler. We're going to need to create the interrupt op when we see that instruction and then implement that op. For now, we're only going to support interrupt 80, and we're only going to support the exit syscall. So the interrupt number should be 80 and EAX should contain 1. And when that's true, we need to stop our program from running. We're also going to need to turn all of our VM opcodes into the equivalent assembly instructions. There are a lot of ways we could do this. This is really what writing a compiler is all about, right? We have some sort of intermediate representation of the program, and then we want to turn it into the most efficient assembly code that we can. We could spend years and years on this. We're not going to do this in a complicated way. A real compiler spends a lot of time trying to figure out how to use the registers efficiently because they're so much faster than memory. So you want to put the right variables in registers, and when you make a function call from when you go from one function to another because of a function call, you want to preserve your data in registers and have the function you called already know where that data is in the registers. And there's all this work we could do to try to make that efficient. We are not going to worry about efficiency at all here. We're going to do a straightforward translation using the stack for everything. So our VM opcodes are all based around the stack, and the assembly we generate is all going to use the stack in the same way. This means we're going to generate a bunch of redundant code, which is fun. We don't really care about speed here. So push, iload, and istore will push and pop values on the stack just as they do in the VM language. Our binary operations are going to pop values off the stack into ECX and EAX, apply the operation, and then push the result back on the stack. Division and modulus are a little bit trickier than that. This is very arbitrary. We could use any registers we want for this, right? So the reason I'm telling you is so that the code you generate will match what the tests are expecting. But really, we could use, any set of registers. Really, we should probably use the caller preserved registers so that we're allowed to modify them anytime we want. But we could use EAX, ECX, EDX in any combination here. Go-to will need to jump to a label. So we're going to have to put assembly labels into the generated code wherever we're going to have branches, right? Anytime we have a go-to, we'll need to add a label on the line we're going to, and then the go-to can use that label to get there. IfEQ and ifNE will use the EAX registers, so they will pop a value into EAX, and then they'll use compare to 0 to decide whether or not they should jump. So again, we'll have to use labels here. The if compare ops have 2 arguments, so we're going to pop those into ECX and EAX just like we do with the binary operators up here. Then we'll use the compare instruction, and then we can use the various jump opcodes to jump conditionally. So if it was a compare greater than, we'll use the jump greater than. Invoke static will make a function call. Remember, we're using the C calling conventions that was discussed in part 19. After your function call, don't forget to clean up the stack if necessary. If the function has a return value, it will be in EAX when the function returns, and we need to push it back onto the stack, which is where the rest of our code will expect it to be. When we see a return op, if we turn that directly into a return instruction, it would not clean up the stack correctly, right? So whenever our functions are returning, we need to jump to the epilogue code of our current function, which will clean up the stack. There were examples of that in part 19. We'll see some more examples below. And then the label names we generate are going to be our method name, $, and then the opcode index. So if we had a branch that was branching to line 5 in the VM code, that means it's the 6th opcode, the opcode at index 5, right? So the label we generate for that would be, say, main $5. All right, here's some examples. Simple subtract function. Here's the VM code it generates. When we turn this into assembly, we're always going to have our prologue, which will set up the base pointer. So we're going to push the old base pointer on the stack to save it, and then we're going to write the stack pointer into EBP. So this will be at the beginning of every function we translate. These comments won't be in the code you generate, right? These are just here to help you understand the code. iload 0 will go get the, this is a parameter as it turns out, so it's going to be at EBP plus 8. So we're going to push that on the stack. The second parameter is at EBP plus 12, so we're going to push that on the stack. And now we're going to do our subtract, and it will generate 4 lines of code. So we're going to pop a value into ECX and then one into EAX. Then we do the subtraction from ECX to EAX and push the result back on the stack. So our binary operations will always generate 4 lines of code like this, or the div and rem, I think, generate 5 or 6 maybe. And then each function will have an epilogue, and the name will be method $epilogue. And then this cleans up our stack. So if we had had any return instructions, we would have converted them into jumps to this label. And this is going to pop EAX. So we are Since we have a return value, we're expecting the result of the function to be on top of the stack when we get to the end of the function. So we're going to pop that into EAX, which is how we return it to the caller. And then we're going to fix the stack pointer and base pointer back to what they were before this function started. And then we do our return to go back to the caller. Max is going to be kind of similar. We do have some branches here. So our max function gets turned into this VM code. And then when we turn it into assembler, again, we're going to have our little prologue. iload 0 and iload 1 are the same as before. Our compare looks a lot like the subtract. We pop two values. We do our compare. This is a compare greater than, so we do a jump greater. And our label is going to be max $$5. So back here, we were jumping to opcode 5. That means the label we're going to use is going to have 5 in it. We had a push 0, which turns into a push 0. Go to 6 turns into a jump to the label at offset 6. We do need to generate these two labels in our code, so we have the label for 5 and the label for 6. Push 1 doesn't change. This is an if EQ 9, so we're going to pop a value, compare it to 0, and if it is 0, jump to 9. iload 0, again, pushes that value onto the stack. When we have a return in the middle of our function, we're going to jump to the epilogue label. And then down here, we're pushing parameter 1 onto the stack. And there was a return here, but because that return doesn't actually do anything, it's just going to the next line, we're not actually going to generate that return or that jump. We're already at max epilogue, so there's no code needed to get us there. And then we clean up the stack. And then the main method here, this time when we set up our function at the beginning, we have one extra command, which is making room on the stack for our local variables. So here we know we have 3 locals, so we need 12 bytes to store them. So we subtract that from our stack pointer to make room. Then we're going to push 12 and 33 and call subtract. So we push 12 and 33 and we call subtract. When subtract returns, we need to clean up the stack because these parameters were on the stack. So we add 8 to our stack pointer to remove those. And then the return value should be in EAX. So we're going to push that onto the stack. So these 3 lines of code are all generated by the invoke static sub. Then we're going to do the iStore 0, so pop off the stack into this memory location. Notice since this is a local, it'll be EBP -4. The parameters were at +8 and +12 and so on. The locals are at EBP -4 and -8 and so on. So iStore 0 here is popping to that location. Now we're going to call max, so push the arguments on the stack, call max, remove the arguments from the stack, push the result back onto the stack. We're going to then store that in local 1, and then we're going to call max again, this time with 12 and 33 in the other order, and store that in local 2. And then our epilogue looks the same as before. So this whole translation process can be done on an opcode by opcode basis because we're doing it in a simple way. It is generating inefficient code. In fact, you can see some of that here. When we get back from sub, we push the result onto the stack, and then we immediately pop it off the stack into this location, right? So really, we should just move it directly to this location, right? So we should say a move from EAX to EBP -4, right? These 2 instructions could be combined into 1. And that happens every time we make a function call, right? And there will be lots of code like that that we generate. That's okay. We're not worried about efficiency right now, and all we want is working assembly code. So we'll settle for that for the moment.